Hi, everyone. So unofficially, this is the AI housing team, but Gavin wanted us to use AI housing team for our project title, but we came up with a better one, and we'll talk about that shortly. My name is Morenike, and I am the graduate fellow for this project. And here we have Gavin from Iowa State University, Kaylin from Iowa State University, and Angelina from University of Iowa. And I would like to give a shout out to Lizu, our project lead, who is always with us. She has always been with us through thick and thin. And we are really grateful for that. As well, we'll be giving a shout out to Erin Mulanix and Erin Austin Douglas for their input in this project. The title of our project is AI-driven housing evaluation for rural community development. So this title can be broken down into three parts: the AI itself, housing evaluation, and rural community development. The project focuses on objective evaluation of housing stock in rural Midwestern Iowa communities. Many small communities lack the capacity to systematically evaluate their housing stock. So we are leveraging AI to look at methods of evaluating housing stock, and we are focusing on housing features like roof, gutter, siding, and presence of vegetation to reflect or show us what the housing quality for each of these communities are. The goal of this project is to investigate methods for conducting a thorough and objective evaluation of a community's housing stock using AI. And the objective of this project is to conduct a literature review to examine examples of AI applications in planning and housing. This is mainly talking about how our cities using AI to address housing problems or in planning generally. And another objective is to identify study communities and collect data about the communities. To collect housing data, collect data on housing age, and some other information. And as well, we wanted to utilize roof, gutter, siding, and landscape condition as part of our AI analysis. And this is also useful for us to identify homes that may qualify for community assistance programs and for grants or for federal funds. And lastly is we plan to use the results that we get for this year, because this project is a 3-year project, and this is year 1. So we plan to assess the results and recommend the next steps for year 2 of this project. And one of the objectives, as discussed earlier, is the literature review. And we reviewed some of literatures and websites, and part of the literatures and websites reviewed Ames City, Orange County, and U.S. Department of Housing and Urban Development. And I'm combining these three because they have something in common. So when they are doing their housing assessment, they check for condition of grass height, roof, gutter, siding, windows, and some other things, but they have those things in common. And then we use this information to in our own project. Then turning data into equity is more is what happened in Detroit, and this is more of community engagement. And we decided to review this because they involved 150 residents in surveying a particular community. And this shows them which community, which neighborhood needs the most attention, needs the most fund. And yeah, then for roadboxes is more of a private company, but we felt their app and what they stand for is useful to our project. And roadboxes is a technology that identifies the condition of roads. So they use a live road imagery to tell us the condition of roads in a particular neighborhood. And this way, it is easy for us to see if this road needs attention, and it promotes safety on roads. And for Macy City assessment, we had a session with Tara Brigman, the assessor for Macy City, and she talked about how Macy City use different platforms to gather data, Beacon and Vanguard. And as well, she talked about the appraisal process that Macy City uses for housing assessment. And one other important thing she mentioned was during housing assessment, they prefer to get a second opinion from an assessor to reduce bias. And this is also one major part of our project. This is the subjective evaluation of housing stock. And lastly is the Des Moines Neighborhood Revitalization Program. And this is also the same thing we've been saying. Des Moines is using AI to assess housing conditions. And moving on to our workflow. The image is just a summary of what we plan to do. So this image is not the actual image we had. So we finally edited to fit in to what we finally did. So the summary of this is we started from image gathering, which is also the same thing as data collection. And we moved to what can we use all these images to do? Images of good houses, poor ones. And then we use AI to identify damages in houses. And this is used to create a database that has information about addresses, the picture, the image of the house, the parcel number, year built, and some other data. And this is just one part for a house. And the database is linked to a neighborhood. So at the end of the day, we want to have a database that has data on a particular house, but also a particular neighborhood or community. And as well, we used the database to assess housing quality, but we focused mainly on roof, gutter, siding, and presence of vegetation. And we'll be moving to data collection section.
Okay, so first we started off with data collection. We wanted to gather images of houses, so we used a website called Kaggle to do so. Kaggle has a lot of useful data sets for building AI models. That's why we decided to start with Kaggle. But later we realized that we wanted more relevant images that were specific to the state of Iowa. So that's when we decided that we wanted to web scrape from other sources. And a lot of the images of houses that we collected were from the Winvest project, which is another DSPG project. And so for data collection, we decided to focus on the same cities from the Winvest project, which are Grundy Center, New Hampton, and Independence, Iowa. So a little bit about web scraping. It's a digital tool that allows us to automatically collect information from various websites, and this type of data collection goes by a lot quicker than if we were to do so manually. So we plan to scrape websites for images, addresses, and house attribute data. The sites we wanted to scrape were realtor websites such as Zillow, Trulia, and Realtor.com, county assessor websites, this website called Vanguard Appraisals, which this company has data for the majority of cities in Iowa, and Beacon is also a very big company that has a lot of Iowa house data. And Google Street View is the last website. Later, we realized that Zillow actually owns Trulia, so we just chose to scrape Zillow rather than both Zillow and Trulia. And ultimately, we collected data from Zillow, Polk County Assessor website, Vanguard, Beacon, and Google Street View. We wanted to collect addresses because we wanted to use Google Street View for image collection. And to do that, we needed to get addresses of houses. So unfortunately, it's kind of a list of addresses and other house attribute data are very hard to come by, especially for cities in Iowa and smaller towns. So this is why we plan to scrape data, so we could just basically create our own list. Like I said before, Vanguard and Beacon are companies that are used by a lot of cities in Iowa, and they hold much of the state's housing data. We tried to scrape Vanguard, and Vanguard has a GIS tool that allowed us to select parcels in certain cities and download information, the information being addresses and parcel numbers. But Vanguard only had data for the city of Independence. And one thing that we noticed was that Vanguard limits the number of parcels that we can select at a time. So when using the tool, we had to make sure that we weren't selecting the same parcels, things like that. And then Beacon, when we tried to scrape Beacon, we found that it was much more protected against web scraping than Vanguard. And also the GIS tool was not available for the Beacon data, and the others, Beacon had data for Grundy Center and in New Hampton, Grundy Center and New Hampton. But the thing is, we didn't want to download the data one house at a time. That would just take way too long. As an example of how long this would take, the city of Grundy Center has about 2,000 people, and there's approximately 1,200 addresses. So you can imagine collecting data for 1,200 addresses without automating the process would just take way too long. So we found a way to scrape data from Beacon using the instant data scraper tool. And this tool gave us CSV files of the house data that we wanted. So once all the data had been scraped for Grundy Center in New Hampton, we looked at the files and realized that the format was just really weird. So we would have to fix that. A lot of the cells had hidden characters in them. There were new lines within many of the cells, and a lot of the data that we wanted to be separate were just all clumped together for some reason. So we used Excel tools and Excel functions to fix those issues. And then also, after reformatting the data, we wanted to create links that we could use to collect images using Google Street View. So this is an example of a link that we would use to collect an image from Google Street View. So we had to create these links using Excel functions. And then now Kayleen's going to talk about image collection.
The images for our project were taken from 4 sites: Zillow, Google Street View, Winvest, and Vanguard. Before we started collecting images, we wanted to come up with a standardized naming convention to maintain efficient organization, since we are scraping from 4 different sites. In general, the first letter of the source or city represents it, but Independence and Hampton were adjusted to use the letter D and H respectively. And here's just an example of our naming convention. And if we run through an example of it, if we have the source Zillow, the city New Hampton, and the address 311 West Main Street, the resulting image would be named ZH311 West Main Street. So then we went on to scrape Zillow, and to scrape Zillow, we downloaded the image URLs for the for sale houses and the recently sold houses. And in total, we were able to grab about 100 homes or home images from Zillow. And there are many more images on Zillow that we just weren't able to scrape, and we'll get into the challenges here. So the good images on Zillow are only available for sale houses and recently sold houses. All other images of houses on Zillow are just taken from Google. The images for the houses are also stored in a carousel, and the only image we could scrape was the first one, which wasn't always an image of the exterior. Sometimes it was an image of the inside. And finally, Zillow had lazy loading. And the term lazy loading refers to how a web page loads its data. And because Zillow is lazy, it only loads the image data when the user scrolls down the page. And when we're web scraping, we can only download the images that are loaded. So a more complicated process is needed to scrape the entire page on a lazy loading website. But if you're able to get around the lazy loading issue and grab all the images from the carousel, Zillow's a great source for images because they're usually more updated than other sources. So after we scraped Zillow, we went on to scrape Google Street View. And a Google API key is required to scrape images from Google Street View. It's included in the image URL and it allows specific viewing of a house. So as discussed earlier, the address data we collected for Vanguard and Beacon was cleaned and stored in CSV files to create the image URLs for Google. And we wrote code to open each image URL in the CSV file and then download the image. And the challenges of scraping Google Street View, we ran into quite a few, actually. The first one is that image downloading takes a lot of time. For a community of just 2,000 people, it can take over an hour to download all of the images for every address. We also ran into a problem of blurred house images. A lot of homeowners request Google to intentionally blur their homes to respect their privacy, and any image that was blurred, we just had to ignore because it wouldn't work for our AI. We also had problems with address inconsistencies and independence that were causing errors. And those were like multiple house numbers for one address, as in 100/101 or 100.5 for an address. And we were having duplicate images show up for different addresses. And in New Hampton, some streets were just not mapped. And so there was no Google Street View images available, as you can see on the left. And then also images of inside of stores were showing up for an image of an exterior of a house. So finally, for data collection, we collected some attribute data, and we used a spider to collect that data. And a spider is an automated version of web scraping that automatically goes page by page on a website, and it reduces the manual involvement in the scraping process, so it makes it more time efficient. And our friend Aaron Case on the AI Local Foods team made our spider for us, so we could scrape parcel number, image URL, house style, year built, square footage, and appraised value from Vanguard. And once we had all of our images and all our addresses in our attribute collection, we could go on to the AI models. And Gavin will talk about that.
So there's links here for more specific explanations of how our models work, but I'm going to skip these for now. So I want to start with explaining just how AI works for anybody that hasn't touched AI at all. We use image classification AI, which generally works with you feed it in a bunch of images and it will look at attributes within those images. So it'll look for edges or it'll look for textures and try to find patterns between different images. So then when you feed it new images it hasn't seen before, it will be able to identify characteristics that you trained it on. So a common neural network to build for image classification is called a CNN, which is a convolutional neural network, which I have an image down here. You have multiple layers of code that people like to describe it as a brain where you have multiple layers neurons that it will train through the entire image. This image shows, obviously machines can't just see a picture like we do. So instead of colors, they'll see numbers representing those colors. And that red box can shift across the image and try to find, it'll use numbers to find the edges rather than actually being able to see the image. So the convolutional layers will constantly look through these images and try to find patterns with them. After building the model, you have to actually train it to do something. You do this with data. We used, what is it? Can't think of the word. It's when you have you can either have a preset data set or you can have it learn on just a data set that's not sorted. So we had pre-sorted data sets for it to train on. So we had for house present, we had a folder of houses in the picture or no house in the picture. Another option for AI models is you can just give it a big folder of images and it can just find its own characteristics, which we talked about this later. Sorry. Yeah, supervised and unsupervised. Training images. The biggest problem we faced is we could not find enough training images for the poor characteristics of houses. So like for the house not present, most of the pictures we get of addresses are going to have a house in it. So for the house present, for example, we had 400 images of house present and 100 images of no house present. And our initial models we built had about 200 images for each, or it had about 400 images in each bucket, and it worked pretty well. But we found that when you go between 50 and 200 images, you don't train the models as well, as housing pictures are very complex. And this is the most efficient method we found to sort. You just open up a file explorer and just push it into different folders, and it took many hours to sort for all of our models, and it's very time consuming, but it's necessary. Google Colab is the main tool we use to code all of our models. It's just an online Google tool, has Jupyter notebooks, and it's very friendly for people that aren't very familiar with setting up environments. And I have 2 videos linked there that helped us create our first models. So all of the first 7 models we built was built with using the library TensorFlow and Keras. And I'll just give a short overview. We use 70% of our data for training data, 20% for validation, and 10% of testing. So all of that is just for training the models. It will use 70%, it will try to find characteristics, 20% making sure that it actually is training properly and testing to see how accurate the model has become. We're able to just see here, these images are kind of small, but it'll just show you what the buckets are of poor siding, good siding, chipped paint for the siding model. And these are the actual layers of the neural network. So we actually have to add each individual layer we want in the model. So these are the convolutional layers. So we start with smaller layers and we just keep layering them on top of each other, trying to find the patterns. And then, as I said, you have to train, and there's ways to optimize the training. So when you have large data sets, it can train faster and it only takes a few minutes rather than upwards of an hour if you have too much information. These graphs, this shows the accuracy and loss of the models. So the accuracy obviously is how accurate the models are performing, and loss is how close the prediction is to the actual value. So if we have a binary model, it'll return a value between 0 and 1. And if it predicts an image to be 0.7 and the image is actually 1 because it's a house present, then the loss will change on that. And you're trying to get accuracy as close to 1 and loss as close to 0. So this was our actual data, and you can see there's quite a difference. And we think the reason that our data is like this is we have not provided the models with enough data to train on. So it's a little janky right now, but as more data is fed in, it smooths out a little bit. And this is a problem that we have to watch out for the future, where if you train on too much of just the training data, the models can become overfitting, which means they're very good at predicting what you trained it on. But if you feed new images, it can't identify it very well. And how do we use the models? So we made 7 models for predicting on houses. The first 3 were image quality models. So we had a model that predicted, or it could see if there was even a house present in the picture. We had a model that would see how obstructed the picture was, and we had a model that would see if there's multiple houses or just one house. And the idea between these first 3 models is we want the best image to evaluate on. So we don't want to evaluate on houses where there's no picture, obviously. And if we have multiple good pictures, we want to pick the one that has the best view of the house and doesn't have other houses in the picture, so we don't have any mistakes. Then we have 4 attribute models: vegetation, siding, gutter, and roof, which just look they evaluate that specific attribute of that house, and we return this all to a CSV for later evaluation. Other models we built models using the SHAP method, which stands for Shapely Additive Explanations. This comes from the Shapely value, which is a game theory that looks at how the overall cooperation of a team, how valuable each player is. And we can apply the same theory to when a model is looking through a picture, which neighborhood of pixels most influence the prediction of that model. So you can see the layers here. We have almost twice as big of a network that we built. But from that, we had a much better loss in accuracy because we had almost a 0 loss and a 1 accuracy. So it became much more accurate, and it was training on the same data as the previous models. So you can see here, this is the Shapley method. It's looking at, for this house image right here, it's picking up some of the house. It's kind of looking at the trees and how you can only see partial of the trees, and it predicts that it's house present. But we go to this different house image, and it's not looking at the house at all. It's only looking at, it sees that the trees are only cut off at half. So this is really good that we got this working, because it shows that the models are looking at the trees and saying, oh, I only see half a tree, rather than there's a house here. So this is good to know, because we need to feed it more data so it understands that we don't care about the trees, we care about whether there's a house in the picture or not. And our final model we built is we used PyTorch as our library instead of TensorFlow and Keras. And CAM stands for class activation mapping. It's very similar to SHAP, except you have this heat map kind of image that can show up, and it shows the same thing. Our first model, we used ResNet and ImageNet, which is a pre-trained model and a preset data set. And we just used pandas as an example to make sure it was working, and it was. We got a very good picture of it showing a panda. So we wanted to apply this to our own models and our own data set. So we built it in Python. We used PyTorch, and as you can see, towards the end of the model, it started to pick up, maybe there's a car in the picture and this indicates a house, or maybe because I only see trees and I don't see anything else, it's not a house. But we weren't very satisfied with this because it just looks like random blotches and there's no proof this is actually predicting or following the model at all. So we used images of cats and dogs to show that the model is working. We just need more data. And it's cool to see this because you can see it's actually looking at the face and it doesn't have random blotches around the picture. So as we get more data, these will be very helpful methods for us to understand what the models are doing when they predict. And maybe if it says there's a good gutter, we can look in the picture and see if it's actually looking at the gutter, if it's looking at the trees. Finally, you can track the confidence of the models on how confident it is in its prediction. So this is just a graph showing the difference of how confident the models were versus how accurate they were actually predicting. And the accuracy is not super important at this time because as far as we know, it just predicts that there's good attributes every single time, and it's usually right because we have a lot more good houses than bad houses.
So when we got the outputs that the models provided us, we wanted to see what those outputs look like spatially, and we wanted to look at the location of houses to see which ones were more poor, which ones were good or fair. We did this using GIS, which is a spatial system that's used to analyze and display geographically referenced information. So we just wanted to look at the outputs for vegetation, siding, gutters, and roof characteristics. And in the future, we think that applying spatial analysis and more statistical analysis would be pretty useful for communities to visualize the spatial relationship between the data and visualize clusters. So before we actually started mapping, we needed to geocode the addresses that we had. because GIS doesn't always know the exact location of an address, so we had to provide it with latitude and longitude of each address. There are a lot of different types of software that can be used to geocode. We first tried QGIS, which is an open source GIS software. We use a plugin called QGIS, but it wasn't really working for us. The plugin kept crashing when we would try to geocode, and it wouldn't geocode all the addresses like we wanted. So then we decided to try geocoding in R instead. And that was successful. This is just an image of what the CSV file looked like once the addresses had been geocoded. So the full address is here. You also need city and state to geocode. And we now had latitude and longitude that we could use for mapping. So the first maps we created were using QGIS. This is what one of the maps look like for Slater, Iowa. This is just showing sighting quality in the city. After doing some more mapping, we later realized that we could use Tableau because Tableau can be used for mapping and other data visualization. So it would be helpful for us if we had the data all in one place and use the same software for all our visualizations. And ArcGIS was also another option that we were considering. You need a license for it, and it was just more useful for us to use Tableau for these visualizations. So I will just show what the dashboards look like once they were complete. Just gonna scroll down. So one of the cities out of the three, Grundy Center, had the poorest sighting quality and gutter quality. So I'll just show that one, and I don't know why it's not loading. Oh. So you can see what the quality in that city looks like. And you can kind of just move around and see which ones have like good gutter, poor gutter, etc. And we also think it might be useful for communities to be able to compare their city's house quality with other cities. So this is kind of a house quality comparison between Grundy Center, Independence, and New Hampton, Iowa for siding, roof, landscape, and gutter. And you can also interact with these maps. That's also why we chose Tableau, because it's easy to embed interactive maps. And now moving on to demographic analysis.
Identifying housing issues in rural communities requires more than just looking at the physical and locational characteristics of its housing stock. To have a more complete understanding of the local housing issues, we need to look at the community's residents as well. So after consulting with our clients, we came up with a list of demographic and economic measures to help characterize our cities. And we developed a demographic profile as a result of the three Winvest cities, Grundy Center, Independence, and New Hampton. So demographic profile is a type of demographic analysis that focuses on just one area. And it's built using demographic data, and your options for that data are data on age, race, ethnicity, gender, marital status, income, education, and employment. So we use the following demographic data for our profile: population, median income, median home value, median year built, and home ownership rates. All of our data came from the United States Decennial Census and the American Community Survey. And if you missed the previous presentation, I'll go back over what the US Census and the American Community Survey are. So the US Census is one of the best places to gather data or demographic data because it counts every resident in the United States. It has a very low inaccuracy, but it's only conducted every 10 years. So if you're looking for more recent data, you should look for the American Community Survey. It has detailed demographic data, and it is conducted every 5 years for the entirety of the United States and every year for populations over 65,000. It doesn't count every individual in the United States, so it does have some inaccuracy and comes with a margin of error. And it's best used for data on the changing population, housing, and workforce. To collect this data in RStudio, we downloaded and installed the tidyverse and tidycensus packages. So the tidyverse packages just includes a range of functions that make coding in R easier. It's not necessary for data collection, but it makes it RStudio more user-friendly. The tidycensus package is required for data collection though, because it comes with the get decennial and get ACS functions, where you can pull data directly from the US Census and the American Community Survey. To visualize this data in RStudio, we installed 3 more packages: ggplot2, scales, and ggthemes. To go over the ggplot2 package, it's required to make a plot in RStudio because it gives you the ggplot function. And there are several geoms you can attach to the ggplot function to create a plot. And here are some examples. We have geom line to make a line graph, geom point to make a scatter plot, geom histogram for a histogram, geom bar for a bar chart, and so on. There's many more geoms, and they're just as intuitive as these ones. So using the packages and functions above, the following plots were made in RStudio. We're going to analyze Grundy Center, as according to our AI, it has the lowest housing quality conditions. So from this plot, we can see that Grundy Center has a percent change in population of 7.7%. It is about the same as the percent change for Iowa and the Midwest. And interestingly enough, New Hampton has a negative percent change, and Independence has a fairly stable population change. So the percent change in total population is not reflecting on the housing quality. It's not an issue in Grundy Center. This population projection plot shows that Grundy Center is actually the smallest community out of our 3, and that could help explain the housing quality issue, as smaller communities have a smaller tax base and less money to fund neighborhood improvement projects. This home ownership rate plot shows that Grundy Center has the highest home ownership rates of our 3 cities. It's actually been higher for the past 5 years, and it is higher than all of its contextual areas, Iowa, the Midwest, and the United States. So home ownership rate is also not a problem in Grundy Center. For median income, Grundy Center's median income is about the same as its contextual areas. It actually surpassed the national average in 2019 and has stayed higher since. In contrast, Independence and New Hampton especially New Hampton, have significantly lower median incomes compared to its contextual areas. So median income for residents is also not contributing to the housing issue in Grundy Center. The median home value for all 3 communities is roughly the same. Grundy Center's median home value was actually the lowest in 2009, and it has since risen to have the highest median home value. And this year structure built graph is our final one. And we know that Iowa has a very large percentage of older homes, and that is definitely reflected in our 3 communities. Overall, Grundy Center has the youngest homes, and it actually has at least 1 or 2 homes that were built in 2020 or later. So Grundy Center is close to the Cedar Falls Waterloo metropolitan area. So that could help explain the fact that our AI is showing it has a low housing quality, but it also has a high growth rate, median income, and housing value. There may be demand for housing in the community, and the residents may be traveling to the metropolitan area for work, reflecting in their median income. We created a couple other visualizations using the infographics feature on ArcGIS Pro to create community summaries of Grundy Center, Independence, and New Hampton. These visualizations are an easy way that communities could gather data very efficiently for themselves. And a community summary is a base template on ArcGIS Pro, but you can add custom demographics if needed. To keep this project moving into the future years, we wanted to identify study communities in Iowa that could benefit from our project. So all the data collection was again done in RStudio using Tidy Census and Tidyverse packages, and we collected decennial census and American Community Survey data. And we collected data on the age of the community. We wanted to know the age of the community's population because it can really tell its growth. If the community's population has a higher percentage of individuals over 65 than they do under 18, there could be a problem with younger generations moving away, and the median age could also indicate that same issue. We also looked at population size. Specifically, we wanted to look at communities with a population of 500 to 10,000, as smaller rural communities are our focus. And we wanted to know if that population was declining, as that can also indicate it's struggling. We also looked at housing data. A low median house value and high median house age can indicate struggling. If a community has a high median house age, there could be a lack in new housing and a community is not growing. We looked at occupancy rates. We wanted to know if there was low home ownership rates and high vacancy rates. And if there's little room for investment, if the residents of a community cannot afford to own their own homes. We also looked at income, because again, if residents have little income, they will have little room for community investment. And then finally, we looked at jobs and employment data. Employment statistics were very important because there was only money to invest in a community if people are employed. So the percentage of the workforce that commuted to work gives information on where jobs are located. If people are commuting, there are not enough jobs in the city. And the problem is that people tend to move where jobs are. We were able to start the visualization process in Tableau. Here is a graph for our population data. We were particularly concerned with population or communities that fell below average for percent population change and below average for population size. Those communities would be potential study communities for future years. But there, as you can see on this graph, there's a lot of cities that fall into that area. And so further analysis with our other data that we gathered will be needed to narrow down which communities in Iowa would be great study communities for our project.
In conclusion, we can say the project successfully achieved its objectives, starting from the review of literature to AI analysis. And we think the project can assess the results and recommend some future research questions that we think can be useful for year 2 of this project. And the first one is, could we use AI to determine which communities could benefit most from our project? That is, for instance, we can provide AI model characteristics of a particular community, and it can derive conclusions and determine which community should be our target, which communities need the most assistance. And the second research question is, could these types of tools be developed into an application and used by cities to evaluate their housing stock? Is there a relationship between neighborhood housing quality and access to school, healthcare, and food? Then we think year 2 can leverage spatial analysis tools and identify communities that can benefit from this project. And an example of the spatial analysis tool that we recommend is Geospatial Analysis Intelligence, which is GeoAI. We also think they can harness GIS better than we did for this year. Then the image is an image of the drone session that we had in DSPG, but we think the idea of drone to GIS can as well be adapted in year 2 of this project. That is, can we create an AI model that can identify houses, trees, sidewalks, and evaluate condition of a neighborhood if we feed it in? This is a neighborhood. What is the condition of this neighborhood? And can it give us a result of, is this neighborhood, do they need assistance, grants, or federal funds? And the last image is just an image of what Chris is still working on, and he promised us he would complete it for this project, but we hope by year 2, he would have completed this. So it's just an image of, he thinks if you click on an image, it should bring out the image of the house. Instead of tweaking or anything, just click on it and it will bring out an image of the house. And the last thing is data source. If you want to read more about the data sources that we use, these are the ones we used. And the recommendations that we included in this project is mainly for the interns and the fellows that will be working on this project for year 2. And that's all. Thank you.
So you're showing your graphs for New Hampton, I think. In trying to look at like what potentially factored into why there was more poor quality houses there. Right? Was it New Hampton? Yeah, starting here. You can go down. Yeah, right here. Yep. So you showed a bunch of things, but did you ever find anything that you thought was driving that?
I think mostly that Grundy Center is a smaller community, and that it is next to Waterloo and Cedar Falls. So it has a metropolitan area that could be allowing the residents to commute to work and have a higher median income.
Okay, so it was for Grundy Center then, not New Hampton.
Yes, for
Okay.
Grundy Center.
So the one that you noticed was the home ownership was different for that?
Yeah.
Could there be something about home ownership that's also causing the quality of the houses to be poor? The fact that more people are owning their homes but not investing in the. Do you understand my question?
Yes, I think so. Does anyone have?
I was just thinking that like if you're renting and the person who's renting the house has to keep it to a certain quality. But I don't know if that is actually true or not.
So I know that this is the first year of a 3-year project, but just thinking forward, and you presented also the information that you plan to share with the next group, which I think will be very valuable. What I'm just trying to think through the community lens. When this project is sort of wrapping in 3 years, what do you hope that the communities gain from the insights and information that you're sharing with them?
I think that would be like an app, like grocery stores made that can, if we feed it the details of a community, it might be an address, and then we tell it, oh, is this neighborhood, is the housing stock in this particular neighborhood good? Should we focus on this neighborhood for assistance programs or not? I think the app should be able to tell us that.
So I thought I was thinking it'd be really cool if the app could, not only can you get street view images and we collect images from Winvest and Beacon and every single thing we get. So not only can we evaluate the front of every house, but maybe if we have a neighborhood, we can do something like this where it counts the number of houses, it sees what's in a park, if there's sidewalks. So it's very similar to what we would do for Winvest, but it would be automated. So a city they can get evaluation of their entire house, and then they can also see what's in the house without people actually having to go and walk around. There's just satellite that will do it for them, and we just have AI models that will find it.
So we have a comment online that says it would be interesting to see how the AI scores and reports for a community would compare with a traditional Windshield housing condition assessment report. And yeah, I know the Winvest project where we did a windshield condition or housing condition assessment with our feet and not in a car, so no windshield. We use those scores to help build our AI and train our AI.
The other thing I can add is, okay, using AI could, the idea behind AI is to reduce the subjective nature of housing assessment, of housing condition assessment. And traditional assessment would definitely be an objective one. So I think that would be a plus on the side of using AI to do that.
Well, it'll also become, it's much quicker to have a model just run through the internet and collect a bunch of images rather than having, like, we've talked to one of the assessors that said it takes months to do these assessments. And if we're able to automate this process, even if the models aren't working perfectly, if they're working at a 90% accuracy, that still gives them maybe 30 houses that we can say, you can go look at these houses and see if there's an issue with them. So it goes much quicker, and then a city might not have to go evaluate their city. They just come to us and they're like, hey, just evaluate us.
The other thing I think that's going to happen, we've talked about this, is every now and then you get these federal or state, whoever, or nonprofit grants. Short lead time, you got to turn around, you've got to do the assessment, but the assessment, you're using data that's a couple of years old. They want recent stuff or post disaster or impact. If there's a way that we could do this, they're using Google here, but back to that windshield survey, if there's another way to capture those photos real quickly and just have the photos that you can drop into a directory, like we did at the Fulcrum, that having then an AI tool that can help do an assessment to understand what is the impact, that you can then turn around, take those numbers and put them into that grant and get it submitted. The timeliness of that could be really beneficial to these communities. Yeah, so not quite yet, Omar. This is year one, right?
Well, so the accuracy on average is around the 80% range, but we don't actually trust that because as far as we know, it's just saying that there's good attributes every time. And since most of the houses don't have issues, as far as we know, the AI has no clue what's going on. It's just saying that there's good houses. So I'm guessing we're probably around 60 to 70%, but as we get more training data, it should become more accurate. One thing me and Sadat talked about is there's a possibility that the AI model is very confident and it is actually completely wrong. And as we give it more data, it's going to realize it's wrong and then lower its confidence and then it'll go back up.
I mean, it all comes down to the data, but also the thing, we're talking about the tool that I haven't got built yet, is they were focused on exact communities that we were working with or we were on the ground in, which was part of the ground truthing that was happening. And that usually doesn't happen until a bit later on in this model building. So that came a little bit earlier on than we expected. But I know that there's homes in other communities when you go driving by, I mean, oh, I need a picture of that one, and you can't get it. The tool down here, hopefully we can go back and get the Google view picture of it, but part of just identifying where are some of these structures that would actually help us train the model. And there may only be 5 or 6 in the entire community. And so we're gonna throw out to our, when we get some stuff built later on this fall, we'll be throwing out to our own staff. If you know of photos or areas, have a tool to then go just capture it for us so that we can start to build up this library that Gavin's talking about. Yeah, okay.
Just coming back to like the confidence of it and then also the windshield comment. It would be interesting if we could take a community that has had a windshield and then compare to what the AI does and then start to see, and that wouldn't be, maybe next year or the year after.
That was part of my question. Could you go back to the GIS mapping? I felt like and the cats. Who doesn't like cats? I felt like there was a big leap in the presentation between the cats and the mapping. And I think it kind of gets at some of these questions. So could you talk through, and I know we're past time, but where did the data come from that is being displayed in these GIS Tableau dashboard maps?
So when we had the big program that would run through all of the models. So if we have an address, it will say what it thinks quality of vegetation, siding, gutter, and roof is. And it will export that to a CSV and join that on the address. So every single address in these cities that we have any image for, it will evaluate the qualities. So a lot of like what our model are saying is there's a lot of good siding and that will print, but that's purely based on how well the models are performing now.
Okay, so this is the AI mapping of the conditions. It's not the WinVest survey information.
None of this is from Winvest.
Okay.
Just the AI, but so when the AI was put stuff on the CSV, some of the models look for if a house is present or not, and things like that. It will like kick out those images and won't evaluate those ones. So there are actually a lot more points on the map, but we just excluded those just to show the ones that were actually completely evaluated. Some of them, I believe the AI might have said certain things and kicked them out for, even though like the reason wasn't correct. So there might be some exclusions on the map.
So could you go and map in each of these conditions those properties that got kicked out?
Yes, we can.
Are there circumstances where they were kicked out for not being able to read roof quality, but were read in gutter quality?
So the attribute models, if a picture made it past the first 3 models, it is guaranteed to get evaluated by the other 4.
Okay.
But a common issue was every now and then a very blatant picture of a house, like it wasn't obstructed, it was obviously a house, it'd get kicked out. I think we tried to go a little over on the data. We tried to not only see if there's a house in the picture, but we tried to make sure that it wasn't like a gas station or something, which this works pretty well. Like a lot of gas station pictures and store pictures would get kicked out, but at the result of that, since we don't have enough data yet, it will kick out some of the normal houses
Got it.
accidentally.
Got it. Thank you.
Did you do a comparison between WinVest results and the AI results, the ones that matched?
I don't think we did. I think the reason we didn't is because we tried to use the WinVest photos for training data. because they were more accurate. In New Hampton, we had barely any addresses, so we used a lot of information from Winvest to train. So we would need a new evaluation because we just sucked all that data into the training. Or we would have to retrain it with different data to use the Winvest to compare how well it compares.
Just comparing address to address, what result came from Winvest to the AI? Yeah, it's just,
So, yeah, so if a student said that there's poor housing, or if there was a poor roof, and we use that to train the model, and well, if we run the same image through, it's going to say that that roof is poor because that's what we trained on, and it will know that. Yeah, they should all match exactly. Yeah, so I don't think this project, we cannot eliminate bias because we still have to physically sort the images to train it. So the only way we can get around this is if we say this is exactly what we looked at to sort each image. Like if the roof has minor damages, it's damaged. So we would have to go through, but it doesn't eliminate bias. It more of just gives a consistent rating for each model.
So the goal isn't necessarily to eliminate, but to reduce bias. But at this point, there's just not enough data. There's going to be bias. I mean, there's so little data for the training. There's going to be bias in it, but you add 10,000 more photos, and these were data points being entered in our case by multiple students that were doing this. That alone is starting to reduce a little bit of bias because we have multiple inputs. What would be better is if we had 3 or 4 people evaluating the same property. And if it's consistent, then use that to train. But this right now, for the first year now, they have a process. So part of next year might be go add to that process and have multiple evaluations and then use that data to train it. But again, that's going to take a lot more people hours and a lot more photos. Okay.
Thank you for allowing me a second question. But as we plan to next summer, I was curious during your process, if there was a data set that you were like, gosh, if I just could find this data set, it would make something so much easier or better.
I didn't have a data set that I wanted to look at to make things easier, probably making it harder, actually. I wanted to, it's one of our recommendations for next year to look at the location of healthcare, daycare, schools, grocery stores, and like retail to, because we know from other data that thriving rural communities usually have 1 or 2 of those features next to them. And we wanted to know, like, if they are lacking in those features, is their housing quality lacking as well?
Oh, okay. So, so firstly, well, I'm super interested in the image CNN model that you did, and I think, well, you did such a awesome, wonderful job. But then, well, let me ask you this. For that image of the house that you have, how many data point that you have right now in your training? I mean, is it like 1,000, 10,000?
So we have thousands of images of good houses. For that specific image, it was the house evaluation model. So we fed it data for house present or not. There was 400 images of good houses, and there were only 100 images of poor or no house present. So we obviously need a lot more to train on because houses are very complex pictures for it to try.
Yeah, so please allow me to throw in an idea here. So I know this kind of problems and those like deep learning problem for images, they're such a data hungry. So 400 is not gonna cut, and then you need something like a millions. But then how can you get those like millions pictures of houses, and how you're gonna like manually label them, put into a folder? They're gonna be such a humongous job, right? So instead of doing that, let me throw in some idea though. Initial idea. So how about, so if you look at something like Zillow, everybody knows Zillow, right? And then they're famous on some estimation like Sestimate, right? But the Sestimate is kind of crooked though. So for example, if, well, what they're trying to estimate by multiple things, by multiple features. But then once that particular house put on sales on the market, if it's like much higher, then Sesame would jump right away. So it's kind of like they add like the knowledge into, and it adjust the number, because now they know that, oh, hey, my assessment is pretty far off, right? In the same way that like a stock advisor, a stock analyst, they just like when the stock go up, then it's just like, okay, I was just gonna adjust accordingly and then pretend that I'm already predict correctly. So based on that, I think, well, your problems, you need a lot more data in order to get those like CNN image processing working better. But then if you work with particular cities or small subsets, small areas, then we're never gonna get that amount of data. So instead of doing that, how about you don't do classification directly, but if you collect the data from like national data set, maybe Zillow or maybe like Google Map, and use those like Sestimate and other like number that is already available for like national site. It's going to be like millions of pictures, right? And then you train the model, and the result become like more regression site, and the result maybe become as like a score, a weight. Like for example, hey, this house looked like something like this. You will add some certain points, and a house looks something like this in your training result. You deduct some certain point, and then now you can apply those score back to like a smaller areas. Well, we don't fit to the actual price itself, because like different cities is all different price, but we get like plus and minus point weight instead. And then when you apply back, then you compare to like the current assessments price, then you kind of get a predicted number. And this system will become, instead of become like a absolute classifier, it could become such a recommender instead. And then now human can pick up the rest based on those recommendations, and then they can decide to whether send people to actually look at the place or something else. So, yeah.
Something that I tried initially when we were trying to find images of poor houses, Polk County Assessor site is one of the few that lets you do bulk download of their assessment data. And they also have their assessor ratings of the overall quality of the house. So I had this brilliant idea that I was going to try a regression model to find instances where my predicted value of the home was significantly different than the assessed value. So I would know, the square footage, the number of stories, how it was built. And I thought with those modeling results, if I found houses where the assessed value is much lower than I would expect for a house of that size and type, those might be good ones for us to try and find images, because those might be the poor quality houses. So I think that's kind of what you're, using external data, find some predicted values, look at variances between actual and predicted, and then use that for filtering for our image gathering. And it didn't work for me, but I was looking up houses then individually with the really big variances, and I stopped pursuing it because it wasn't working. But I think that's definitely a good suggestion if we could find a better strategy for that.
Other questions? Anything else online?
I'll respond to that because you did provide us with poor, very poor addresses. So there are some websites online that will already mark, like the assessor websites that will mark them as poor, very poor. So we had a couple, there's probably a couple thousand images available to us that were already marked as poor, very poor. And that's the same idea. It's already marked as there's an issue with that house. So it makes it a little smaller because you're not looking at thousands of images of good houses and bad houses. It's most of them have an issue with them. But I would agree. So were you talking about, are you trying to find an overall value of the house to set that into an area? Like if this house has a low Zillow estimate and it has all these other attributes, we can probably assume that the value of this house is lower. So there might be issues with it.
So what I'm trying to say, it's basically you need millions of data points, right? To make it work with this like image processing. Because if you just, well, it's such a tough problems to solve, right? A picture of the house, it could mean so many different things. And you just get the front of the house. A lot of time, the back of the house is the one that is more showing, right? Showing related more to the value. And that is only the exterior of the house. And this is not a new thing as well. So I heard that in some countries, like in French or in some state, they do Google Map, and then they try to tax the house that have like swimming pool that is undeclared swimming pool to try to access that. But that is going to be easier for sure. Now back to this, we need millions. You need millions of data points, but how can we train the model on that millions data points? So my idea was thinking of that we find, well, you can probably be able to find those ground truth from like external scale and with a lot of available images, and you can fit that with some labels, which is already available as well. For example, like estimate or some other already estimated value that it's out there. Then after you fit your model, and then you can have a trained model that is from large data set, then you can now apply or add some weight for like some local communities. Then you can like predict, it's going to be predict much better, I would say. But since it's a little another problem that the target that you have from the bigger scale, it's not directly related to the price or the conditions of the local scale, right? Which in Iowa, and then it's like national. So that is why I'm thinking of instead of doing classification, then maybe you do regressions, and then where you compare the price or the quality of the house, basically the price with the average price on that location, and then turn that into some kind of weight, plus and minus instead. Variation out of the mean price of the median price of each location. And then you use that weight and try to apply back to like local scale. If that makes sense? But it's just like initial idea though. It definitely could be improved though.
And we could tell next year, we could just summarize that and tell next year that's something they can look into.
And one of the challenges is a lot of this is still based on rural housing. And so the number of homes that we have, even as a sample to begin with, is the challenge too. So continue to keep getting more images in there, using it to help. I mean, the AI simply might be being used to help us identify areas of concern. And as we keep working to that over the next 3+ years, the bottom line is we need to start collecting data at some point. So we're starting now, and we're finding ways to collect data, keep adding to this repository of data, knowing that every 100,000 or whatever photos that we get, eventually over time is going to keep helping build up that model, finding ways like ASEC said, to bring in large volumes of data when we can. But that's great. We just have to, but we have to start at some point. So this is a good start. Other questions? All right, well, that concludes then our data science for public good presentation for the day. Thank you for joining us. If you're online, thank you for joining us there.